So here we are with this cyclist right now, trying to understand what is Newton's second law of motion. Now Newton's second law of motion is related to momentum, right? So just remember, what is the formula of momentum? Momentum is equal to mass into velocity. Momentum is denoted by P, mass is denoted by M, and velocity in general is denoted by small letter v. So P is equal to M into V. So just keep that in mind. Now this cyclist over here, now we know that this cyclist right now is at rest. Now since it is at rest, how much would be the velocity? 0, right? So how much would be the momentum? Obviously 0. That means at point A, the momentum over here is 0. But in order to move this object, in order to set into motion, what do we need to apply? Force, right? So the moment we apply force, we know that this object is going to move. What we are going to do is, we are going to consider how much time is it going to take, and here we are noting the time. So let's say, for example, he applies force and he starts moving from point A to point B. Here you can see that this person has moved and it has taken 5 seconds. But we know for a fact that when he applied force, velocity changed, right? And when velocity changed, can we also say that the momentum also changed? Of course, right? But for that change in momentum, how much time did it take? It took 5 seconds. Keep that in mind. So, certain amount of force was applied, due to which there was a change in momentum, and it took 5 seconds. Now we are going to change the scenario a little bit. This time you can see that we have put a booster on the cycle. That means now the force exerted would be more. Now this object right now is at rest. Now when we apply force, it is going to move. But right now the velocity is 0, therefore the momentum is also 0. But now look at the force. Oh, it just took 1 second. That means when the force was more, obviously there was a change in momentum also. But you can see it took only 1 second. That means the change in momentum was quicker, it was faster. That means when the force is more, when we have more force, we know that there is faster change in momentum. Now what do you mean by this term faster? We know that faster means it is related to time, and in physics we know that when we talk about time, we say the rate of something. That means when the force is more, the rate of change of momentum is also more. So when one physical quantity increases and other also increases, we say that they are directly proportional to each other, which means that force is directly proportional to the rate of change of momentum. So this is nothing but Newton's second law of motion. Now, how do you remember this? How do you memorize this? You need not actually memorize this. This over here, what you see, is actually second law of motion. Now, if you read the statement of second law of motion, we know it is nothing but the rate of change of momentum is proportional to the applied force, and the change of momentum occurs in the direction of the force, which means that in the direction that we apply force, obviously the change of momentum is also going to be in the same direction, which simply means that the statement is simply this. We know that we have the rate of change of momentum is proportional to the applied force. So this is what is the Newton's second law of motion, which simply reads, the rate of change of momentum is proportional to the applied force, and the change of momentum occurs in the direction of the force. So this is Newton's second law of motion. Now with the help of Newton's second law of motion, we have derived a formula that is nothing but the formula for force. Let us see how to derive that formula. Again, we'll take an example and try to understand. So in this example, you can see we have a car right now. Obviously this car will have certain amount of mass, right? That will be denoted by small letter m. Now it will have certain amount of initial velocity as well, since this is the initial position. And what is initial velocity denoted by? U. That means its mass is m, that is small m, and its initial velocity is u. So its initial momentum denoted by P1 would be mass into initial velocity, that is m into u. Now obviously, in order to move this object, what do we need to apply? Force. Let us assume that we apply this force for time t. So it starts to move. Obviously we know that over here this car will have the same mass but a different final velocity, and this final velocity is denoted by small v. So now, since the velocity has changed, will the momentum remain the same? No, right? The momentum would also change, and this time the momentum would be P2, that is the final momentum, and obviously it would be mass into final velocity, that is m into v. So what do we have? We have the value of initial momentum and we have the value of final momentum. Now using these two values, we are going to derive the equation of force, or we can say the equation for second law of motion. Let's start. So to derive the equation of second law of motion, we are going to obviously use second law of motion, which says that the force is directly proportional to the rate of change of momentum, right? Now what is force denoted by? It is denoted by capital F, right? And directly proportional means alpha. Now what is rate of change of momentum? We know that rate means it is related to time, and whenever we have this word rate, we have to divide by time. So we divide by time first of all. Now what would come in the numerator? In the numerator we know we have change of momentum. So how do we find change? Change is always found by subtracting the final value and the initial value. That means final momentum minus initial momentum. So P2 minus P1, because P2 is the final momentum and P1 is the initial momentum. Now we know for a fact that P2 is m into v and P1 is m into u. So we'll substitute the values. So F is proportional to P2 is m into v minus P1 is m into u upon t. Now you can see here m is common. So we have F proportional to m common, and in the brackets what do we have? V minus u, and in the denominator we have t. If you look properly, F alpha m remains as it is. But what is v minus u upon t? This is final velocity minus initial velocity upon time. This actually is the formula for acceleration. So that is the reason we substitute that with small letter a. So F is proportional to m into a. Now how do we read this? We read this as force is directly proportional to the product of mass and acceleration. But from the chapter ratio and proportions, we know that whenever two things are directly proportional to each other, their ratios are always constant. That means F upon MA will be equal to constant, right? So this F is in the numerator, MA is in the denominator right now, because their ratios are going to be constant. This K over here is constant. Now scientists have done certain experiments, and after doing those experiments, when they tried to find the ratio of F and the product of MA, they found that the value was very close to 1. So that is the reason what we do is, this constant of proportionality, we consider its value to be 1 because it was experimentally found that the constant is very close to 1. Now what we'll do is we'll substitute the value. So we have F upon MA is equal to 1. Now we'll shift this MA to the right hand side, that is we do cross multiplication, and we obtain F is equal to m into A, that is force is equal to mass into acceleration, and this becomes the equation of second law of motion, which is very, 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 very important, not only from this standard point of view but also when you go in higher grades. So this was all about Newton's second law of motion and how to derive the equation, that is the formula of second law of motion.
And yes, Please do not forget to like, share, subscribe, and press the bell icon.